your respiratory system, it's going to be based on these two reactions. And you got to remember that this one is going on all the time in your cells. And so they're going to have food that you're going to eat. And I'll actually talk about that a little bit in a little while with the digestive system. But you got to intake oxygen to use the food to make enough ATP to stay alive. So that's just the way it is for all your cells. You end up making two waste products when you do that, though. You make CO2 and water, and while we do have to have water to live, the fact that you are making this water along with the CO2 means you're automatically going to enter this equation down here. There's no avoiding it. So all your cells, just by the mere fact that they're living, are going to be producing protons and bicarbonate. It's inevitable. Okay? Now, as we mentioned before, you get too many of these and it causes serious physiological issues. We'll talk a little bit more about those in a few weeks and how you monitor and change all this stuff. All right? We'll do just a little bit of that. But for now, you realize it's a problem. It makes you acidic. Okay? So the key is, what do we do about it? I mean, here's the problem. The problem is CO2, but we can't quit making it. All the cells have to make it. So what are we going to do? We need to get rid of it. And you're going to get rid of it by exhaling. Okay? And the reason that works is that in the lungs, you get rid of it easily because it's right there, it's leaving. So if you're a cell and you're making this, it'll never build up very much. Because as it builds up, it'll diffuse into the lungs and you'll breathe it out. So you don't have to worry about it. Most of the cells in your body do worry about it. It builds up. So the only hope they have is if they can get the blood to take it away somehow. All right? So when we started talking about this, oxygen's the easiest because the oxygen, most of your oxygen is going to be transported bound to your hemoglobin. So when you have a lot of oxygen, it sticks on the hemoglobin. When you don't have much, it tends to come off the hemoglobin. So if you're in an area where you need it, that means there's not much oxygen there. So it's going to come off the hemoglobin. And the reason it does that is because of this whole affinity thing that we were talking about. Okay? So the conditions are right when you're in an area not near the lungs to where you're going to decrease affinity. If you're up in the lungs, you can increase affinity. That's what that was all about. But the CO2 has an extra complicator in there. CO2, yeah, we can dissolve a little in the plasma of the blood and the water in the plasma, just like we did oxygen, but that's not enough to do us much good. We can bind some of it to hemoglobin, but unfortunately, unlike the oxygen where we can get 98.5% of what we need bound to hemoglobin, we can't do that with carbon dioxide. It's not as efficient. So we can only carry about 23%. So if you only had these two and you're a cell and you're out in the systemic capillaries and you're making CO2, you're never going to be able to get rid of it fast enough with just these two things. It would build up and you die from the acidity. Luckily though, we have another option, and that's turned into bicarbonate. So what happens is as it builds up, it makes it into the blood. It goes into the red blood cells, and the red blood cells convert it into this. Okay? Now, this dissolves easily in water, and so does this. Okay? But you end up actually binding a lot of these things to hemoglobin. We'll actually take that. So either way, now that we have this, and we have this, we can move this in the bloodstream up to the lungs. And then when we get to the lungs, we just reverse it and go back the opposite direction. Okay? So that you can exhale this. And that's basically what's going on. And that's summarized in these two slides right here. Okay? So showing you what's going on in pulmonary gas exchange and systemic gas exchange. So that's what that is. So if we're looking at this, what's happening is, took CO2, for instance, if you're up here, say, in the lungs, well, what happened was you got a bunch of bicarbonate in your plasma that came from down here in the systemic capillary. So you picked up the bicarbonate. You have some CO2 out here as well that you picked up, and you've got some CO2 bound to the hemoglobin. So that's the three ways you transport. Now that you get up here to the lungs, you see there's not much CO2 in the air you breathe, so the concentration stays relatively low. And that means that if the concentration is lower here than inside the blood, the CO2 will diffuse out. Okay. So this is constantly leaving. Well, if that's leaving, that means that there's more CO2 in the cell, so the CO2 in the cell moves into the plasma to replace what left. All right? As that CO2 gets lower in concentration, that means more CO2 will come off the hemoglobin and replace it. It also means that if your CO2 is getting low, then more of the carbonic acid will form the CO2, and that means that more of the bicarbonate in here will turn into H2CO3 to replace it, and so on. So you're just setting up a train. As you start pulling this end off, everything starts moving this direction to replace it. Okay? That's how the chemical reaction works. If it's a reversible reaction like this one is. Now, once you get low HCO3 negative here, what happens is this HCO3 just moves from the plasma into here and undergoes the transformation. So once again, you're setting up a whole train starting from here all the way through so that you can breathe out the carbon dioxide. The thing that complicated the process was you can't dissolve much carbon dioxide in here, so we had to have another way to do it, and that's through this. Okay. All right, two other gases that are kind of important to us. First is nitrogen. Nitrogen makes up most of our atmosphere. It's most of which you breathe. It turns out it's actually not very soluble in water. So whether it's in you or whether it's in a glass of water, yeah, you're going to have atmospheric gases in that water. They're going to go into it. Whatever's in the atmosphere will get into that water. But nitrogen doesn't dissolve well in it, so you'll never get very much into the water. Okay? Therefore, in reality, it's almost never an issue and not anything you should consider, except for one instance. And that is if a person is breathing nitrogen, whether it be pure nitrogen or nitrogen in a mixture, like in the atmosphere, if you're breathing it at pressures that are higher than normal, it can force a lot of nitrogen into you. Okay? The only time we would normally see this happen is in scuba divers or other persons that for some reason would be breathing a compressed air mixture. I can't think of who else would really be doing that at depth. So what happens is when a person is under the water pressure is pushing on them in addition to the atmospheric pressure. Remember how your breathing works. The only way you can breathe is if you can make the pressure around your lungs less than the air you want to breathe in, right? So now you've got a problem because in addition to the regular air pressure on you, now water is pushing in on you. So if you try and breathe regular atmospheric air, you're not going to be able to do it. Okay, so if you're down at the bottom of the ocean, or down, if you're down, 20 feet down or something, and you have a tube that goes all the way to the top, and you want to try and breathe on that tube, well, the problem is that air you're breathing is still regular air pressure. And now you're fighting air pressure pushing on you plus the water pressure. Okay? So in order to overcome this, what happens is they use compressed air so that the air you're trying to breathe in is at a greater pressure than whatever the water pressure is around. Okay, that's how a scuba tank works. So you're breathing in this high pressure air. Well, that makes more nitrogen go into you than normal. That's not an issue under those conditions because you have more pressure on you. There's more oxygen in you as well as nitrogen and everything else. It's okay. The problem is that when you start to ascend and you come up, Now the air pressure on you is less. And the air you're breathing, including the nitrogen in it, is less as you come off. And so what happens is, all that nitrogen you forced into your water in your body doesn't want to be there anymore. And it starts coming out. And it forms bubbles. It does exactly the same thing that your carbonated beverage does. So you have your beverage, you look at it, you don't see bubbles in it. Why? Because it's all there under pressure. When you take the cap off, the pressure goes away, and now the carbon dioxide is usually the gas they use. It's been forced in there. It's not happy there anymore. So it comes out and makes those fizzy bubbles you like, right? Unfortunately, in this case, it happens in a person. And so it starts forming little microscopic bubbles of nitrogen coming out in solution. Okay? That is termed decompression sickness, also called the bends. It's called the bends because when they first discovered it, is when they first started having people breathe pressurized air, doing deep sea salvage and things like that. And the people would come back up on board the ship, and all of a sudden they'd start experiencing all kinds of symptoms, but the most obvious one was they would end up in tremendous pain. It would be so bad that they would double over and lie down on the floor and huddle up like in fetal position screaming. So they couldn't figure out why it was happening. They called it the bends, bend them up. Okay. But now we understand. If this happens to someone, what has happened is they've ascended too quickly for the amount of nitrogen that got in. If you do it slowly, it's like your fizzy drink. If you don't want it to fizz much, you can go wait a little while, again, and slowly let the pressure kind of come back to equilibrium, slowly bleed it off. That's how you keep them from over foaming on it. Same with the person. Now, if they do come up, and they come up too fast though, because there are various serious health issues involved, they're usually not going to send them back down into the water. So what they do is they take them to a hyperbaric chamber and put them at high pressure in the chamber, and it forces the nitrogen back into solution. And then they let the pressure off gradually, so they'll defizz them, right, slowly. Now, once again, many people, many areas of the nation never have to worry about that. But in this area where we have people who scuba dive, yeah, this stuff happens. Okay? So you just need to realize the basic steps here of what's going on. Okay?
Professor.
Yeah.
Is that also the reason why, like, when people like dive and they take their vest out super fast?
They do what?
When they go diving and they come up, a lot of times they will instruct them to take their vest or the suit they're wearing, like, out fast.
Take do what?
Like the suit
Yeah.
they wear, they usually like take them out, like take them off, like super fast. Does that have a correlation with that? Or just...
Not really. They usually just want to get them out of the suit. Now it depends. If they still had pressurized air and something was wrong, yeah, but it should normally happen because the air's going to equalize it, whatever. They usually just want to get them out of the suit because the suits are usually really hot and really uncomfortable.
Okay.
But anyway, there's several things that can go wrong. That's why they had to make you take classes to scuba dive. This is only one of them. There's a few things that can kill you. But this is not necessarily the strongest one. All right, but anyway, just so you understand what's going on. The other gas I want to talk about is carbon monoxide. Carbon monoxide is a serious threat because you cannot detect it in any way with your natural senses. You can't smell it, there's no taste from it, it's colorless. You don't know it's there. The problem with it is that hemoglobin loves it more than it does oxygen. So if there's molecules of this around, it bonds to the hemoglobin. The hemoglobin doesn't like to let go of it. Okay? So it basically takes up all the bonding sites for the oxygen. Usually what happens with a person who comes down with this is they never know anything's wrong. Sometimes they will get a headache. Sometimes they'll get nauseous. Most of the time, they just get really sleepy and go to sleep and never wake up. Okay, so that's why it's so dangerous. This is produced by burning materials. One of the main ways is by using fuel to fuel the generator. And it's more common up north because of the snow and ice and losing power, people use generators, or they use other, sometimes ways to keep warm that involve combustion. And they'll do it inside for a house to try and keep warm or keep the power on. And, that kind of thing will end up causing deaths from carbon monoxide poisoning. Here, it almost always happens during a hurricane or a storm where you have power outage and someone is running a generator right by your house or in their garage. Okay, let's use it in this house. So that's it. Now, when it comes to regulating your respiratory system, we have two things that we regulate. One is the ventilation, so how fast or how deep you breathe, okay? The other would be the diameter of the air tubes that you're bringing the air in and out of the lung, okay? So that's our bronchodilation and constriction. So the first one, though, is regulation of pulmonary ventilation. So we will be talking about either how fast and or how deeply you're breathing. I rearranged this from the first way I had it posted, so you probably noticed that back last Thursday, or Wednesday maybe, I had this new version up. But the reason I changed it is I wanted to make it look more like what you're used to now with the other sections, okay? So this will look kind of familiar to you. So if we're talking about how it works with your nervous system running this, you have afferent pathways, once again, glossopharyngeal nerve and vagus nerves. Carotid bodies, aortic bodies, you've got your chemoreceptors. The difference here is that we have some new receptors. It turns out that your vagus carries impulses from stretch receptors located in your bronchi and your bronchioles. Okay, so they'll have stretch receptors in them that are hooked up to the vagus nerve. And that is going to carry those impulses up to the control center, to the control centers in the medulla oblongata and the pons. Now, the medulla oblongata is pretty much what we discussed before. Not only is it a control center for cardiovascular, but also for respiratory, and it has chemoreceptors there. So it has the same chemoreceptors we mentioned before. It's got proton sensors for pH and CO2 level sensors. For the respiratory system, it's extremely important due to the CO2 sensors because the CO2 receptors are the most sensitive of the ones involved. So they end up being the ones that primarily control your respiratory rates. Yes, you do get control from these, from the oxygen sensors as well, but they're nowhere near as important as the CO2. Right? So this is primarily what determines when you breathe and how fast you breathe and how deeply you breathe. The pons plays a role, but honestly we don't really know exactly what it's doing. What we know is that it's active at certain times, especially when you see the transition from inhalation to exhalation. So it seems to have some control over muscle coordination, but that's about all we know about it right now. Now, whatever decision is made by the medulla oblongata, we've got our efferent pathways that come out from it. And this would be the phrenic nerves, which are cervical spinal nerves, and the intercostal nerves, which are thoracic spinal nerves. So those are going to be the ones controlling the muscles. Okay. Note that these are skeletal muscles, and so essentially what's happening is this would be working basically like your somatic system, and really is part of the somatic. So you're talking about nerve impulse going down, releasing acetylcholine, causing the muscles to contract. So overall, if we look at all of this stuff, how's it going to respond to changes in homeostasis? Well, as far as chemistry goes, if we have high proton concentrations, which would be low pH, or we have high CO2, you're going to increase ventilation. you would do the same thing if we have low O2 levels, all right? So when it senses those, you're gonna increase your ventilation. The mechanical receptors, they're stretch receptors that are designed to fire off impulses as they get stretched, and you have a reflex called the Herring-Brewer reflex that will force your inhalation muscles to relax if they're stretched too much. Okay? So it makes it impossible for you to inhale enough to burst your lungs or rupture your bronchi or something like that. Okay? Because if you try and do that, your reflex will kick in and automatically relax them. Now, that was ventilation, so it's talking about, once again, that's gonna be how quickly or how deeply we breathe. But we can also regulate airway diameter. And the way that works is both through the nervous system and through our endocrine system. The nervous system, as you might expect, we've got sympathetic and parasympathetic autonomic. The sympathetic autonomic is a set of thoracic nerves, thoracic spinal nerves. The neurotransmitter release, this is kind of old news to you in the sympathetic, would be norepinephrine. The receptor is going to be beta 2 type adrenergics, which means when the norepinephrine hits those, it's going to cause relaxation, which would allow bronchodilation. Okay. Parasympathetic autonomic, it's going to be the vagus nerves again. If we're in parasympathetic, as you expect, acetylcholine's neurotransmitter, the receptor is going to be muscarinics. And that's actually going to cause contraction of smooth muscle or bronchoconstriction. Now, most of this should make sense when you tie all of this stuff together in these slides, how it's going to work with your nervous system using your autonomic, your sympathetic, parasympathetic. In addition, we can tie in the next one. The endocrine system, because what you got going on is your adrenal medulla, once again, can release epinephrine, norepinephrine. Those activate beta 2 adrenergics that would be on those bronchioles, the bronchi. And remember, epinephrine is the more effective of the two, and that's going to cause relaxation of smooth muscle, bronchodilation, because that's exactly what's happening here with the norepinephrine. Just this is coming as a neurotransmitter, the other is coming as part of your adrenaline release from your adrenal glands. Okay. And once again, you can put all this stuff together and it should kind of make sense. So for instance, the big bear is attacking you. What are you going to do? How's this going to respond? Well, obviously, that's a situation where you want to engage the sympathetic fight or flight. All right. So what would it be good to do for you? Well, if you're going to have to run from the bear, you already know you're going to increase heart rate and increase contractility. You also know from the last set of material what you want to do with your blood vessels is you actually want to constrict them, okay? Because, yeah, when you constrict, it increases resistance, all right, which restricts flow. But remember, that's being countered by your heart pumping faster and harder. So what it does is it keeps blood pressure up and flow up. And the extra blood pressure means more fluid leaving the capillaries and going into the interstitial spaces, and therefore bringing more oxygen and taking away more carbon dioxide from the cells. Now, while that's going on, that's what you learned for the last two tests. But for this, what about respiration? Well, you want to be able to fight or run from the bear. So what you want to do is you want to breathe faster and deeper, get more air in and out, You also want to relax those bronchi and bronchioles so that you get more airflow. All right? Makes sense? Okay. Because unlike your capillaries, you see, you can increase your heart rate, contractility, and you squeeze down the capillaries, which normally we think would be a bad thing. But yeah, there's more resistance. But with that heart beating so much harder, it's keeping the pressure really high, and that increases perfusion, the amount of bathing of oxygen, everything the tissues are getting from capillaries. We don't have that with bronchioles. Right? There's no capillaries in the bronchioles. There's something around it. So nothing's leaving. You know, your alveoli, the air is not leaving. You get things diffuse across, but you have to push it in and pull it out. So what you want to do there is you want those bronchioles as big as they can be, so the air goes in and out really smoothly. Okay, you're not trying to push it in under pressure so that it somehow leaves, and from the alveolus. You just want to keep it ventilated. All right, that's what's going on. So you can see, I think, from the other two tests that this area is set up pretty much the same as I did for the other test. We just have a few tweaks. You have to watch for different receptors like beta 2s from alphas, whatever else, and you got to remember that we are doing our bronchioles in both cases. So, for instance, you mentioned asthma before. So, asthma is a perfect example of bronchoconstriction, increasing resistance, making it difficult to breathe. Yeah. So, what do they do about that? Well, a lot of the medicines that they use will actually activate beta 2s. Okay. Because if you activate the beta 2s in your bronchioles and bronchi, what's that going to do? Well, it relaxes the smooth muscle. Okay. So they use a beta 2 mimic. I should say norepinephrine, something like that. Okay, that's what Now, digestive system is certainly the easier of the two systems, at least from our standpoint. Now, what you got to do, though, is just make sure you don't get the information confused and you know all the terms here. So, with our digestive system, it's really just a survey of organs, chemicals they produce, what they absorb, that sort of thing. Now, your digestive system organs can all be divided into one or two kinds. They're either part of the gastrointestinal tract, also called alimentary canal, or they are considered accessory organs. What sets them apart is that if you're part of the GI tract, the food or digested material passes through you. Okay? It enters part of you and it goes out another end. The accessory, that doesn't happen. Okay? Food never goes through them. So what we're going to do is we're basically going to start out with the mouth, and then we're going to just walk through these. So all the way to the mouth, to the large intestine, and then we're going to discuss as we move along how the accessory organs are involved. Now when it comes to controlling all this, you may recall from A&P1 that the gastrointestinal tract has its own little nervous system called the enteric system. It is largely, but not completely, autonomous. So in other words, it can run the GI tract on its own to some degree. So I can actually take your GI tract out of your body, all right, keep it in a solution called a Ringer solution, and provide it what it needs. I could put it in a big tray right here on the table, and we could sit there and watch it still continue to digest your food. Okay? Now, this is done by two different sets of nervous tissue called plexuses. One is called the myenteric plexus, and the other is submucosal plexus. The myenteric controls the smooth muscle, okay, of the digestive system. the GI tract motility meaning motion. Okay. So that's what stirs your food and controls movement of the food through the system. The submucosal plexus controls secretions of your glandular cells. So how much mucus is released, what enzymes and how much are released, so it's controlling that. Note, and they hopefully went over this with you in A&P1 as well, but even though the enteric is running the show for the most part, it has connections to the autonomic nervous system. That way, the autonomic nervous system can influence it. And as you might expect, there are parasympathetic and sympathetic connections that go to it. And if it's stimulated by the parasympathetic, what it actually does is increase secretions and activity. If it's stimulated by the sympathetic, it decreases. So this will pretty much